Welcome to the deep dive. Today we're tackling a topic that honestly weaves through almost everything in medicine, lipid transport.
Really does.
Yeah, I mean, imagine you're on the ward, maybe just starting out, and a senior doc points to a chart, talks about dyslipidemia, this cholesterol numbers,
hmm
and suddenly that, dense biochem lecture, it becomes very, very real.
Absolutely real. So our mission today is to try and demystify it, made it stick.
Exactly. We want to turn the facts into like a solid foundation you can actually use. We need to understand how our bodies handle these fats or lipids.
Because they're crucial, right?
Right.
Energy, membranes, hormones, lipids do so much. But, and this is the big but,
They hate water, hydrophobic.
right? And our blood is mostly water. So the central question is, how does the body move these essential but water-fearing molecules around? How do tissues get the lipids they need?
That's what we're diving into. The body's really elegant solution, and crucially, what goes wrong when that system breaks down.
Yeah. We've pulled together the key stuff from, the standard lectures, the big textbooks.
Kind of distilled it down. Think of this as your lipid transport boot camp.
Boot camp, I like that. It's not just memorizing pathways. It's about getting the why behind it, so it connects later when you see patients.
Okay, so let's start with the players. What exactly are we talking about when we say lipids, these sort of problematic molecules?
Well, it's a varied group. You've got the main energy stores, triacylglycerols, TAGs for short,
Right.
then fatty acids, cholesterol itself, and cholesterol esters. Phospholipids, too vital for cell membranes.
Oh, and don't forget the fat-soluble vitamins, A, D, E, K. They need transport too.
Good point. And the fundamental issue for all of them, as you said, is hydrophobicity. They just don't mix with the watery blood.
So if blood's the highway, how do they travel? I know a tiny bit, like maybe 2% of free fatty acids, can grab onto albumin.
That's right, a small fraction. But for the vast majority, the other, 98%? They need dedicated transport. They need these specialized carriers, lipoproteins.
Lipoproteins. Okay, so these are the transport taxis for lipids.
That's a perfect analogy. The taxi analogy works really well here. Let's break down how these little vehicles are built. Think of a sphere.
Okay.
The very center, the core, that's like the passenger compartment. That's where you stash the really water-insoluble stuff, the tags and the cholesterol esters, tucked away safely inside.
Away from the water. Makes sense. So what's the outside of the taxi made of?
That's the clever bit. The surface coat or the shell. It's made of phospholipids and some unesterified cholesterol.
And phospholipids have that dual nature, right? Water-loving head, water-fearing tail.
Exactly. So they arrange themselves with their hydrophilic, their water-loving heads facing outwards towards the blood.
Okay, so they're happy interacting with the water.
Precisely. And their hydrophobic tails point inwards, cozying up to the lipid core. This whole structure makes the entire lipoprotein particle soluble in blood. It can actually move.
Brilliant design. But a taxi needs more than just a body, right? It needs a driver, maybe a GPS, an ID.
You got it. That's the role of the apoproteins, or sometimes called apolipoproteins. These are proteins sitting on the surface, either embedded or just attached.
And they do. What exactly?
Two main jobs, both critical. First, structural. They help package everything, hold that spherical shape, keep the hydrophobic core contained and soluble.
Okay, structure. What's the second job?
Functional. This is huge. They act as cofactors for enzymes involved in lipid metabolism. Or they act as ligands, like keys that bind to specific receptors on cells.
So they're directing the taxi, telling it where to dock or maybe what enzyme to interact with.
That's exactly it. They're the drivers and the ID badges. They determine the fate of the lipoprotein.
Gotcha. And I remember there are different types, peripheral and integral.
Yeah, broadly two types. Peripheral ones like APOF and ApoE are loosely bound. They could hop on and off, be exchanged between lipoproteins.
Like temporary crew members.
Sort of, yeah. Then you have the integral ones like ApoA and the big one, ApoB. They are deeply embedded, part of the fundamental structure of that specific lipoprotein tax. They don't leave.
Okay, so these apoproteins, these ID badges are crucial. But hang on, we've got all these different lipids, tags, cholesterol, vitamins, and these complex taxi structures. It makes you wonder how many different kinds of these lipoprotein taxis are actually out there, and what makes each one unique for its particular job?
That is the perfect question. It sets us up beautifully for our, let's call it, grand tour of lipoprotein metabolism.
Okay, hit me. How many classes?
There are 5 major classes you need to know. We've got chylomicrons, VLDL, IDL, LDL, and HDL.
Chylomicrons, VLDL, IDL, LDL, HDL. Got it. How are they classified?
Primarily by their density, which we measure using ultracentrifugation. It basically depends on the ratio of lipid, which is light, to protein, which is heavier.
So more lipid means less dense.
Exactly. And interestingly, density is inversely related to size. So HDL, high-density lipoprotein, is the smallest and densest lots of protein, relatively less lipid.
And chylomicrons, they sound big.
They are. They're the largest and least dense, absolutely packed with lipids, especially triacylglycerols, with less protein.
So sticking with the vehicle analogy, it's like we have everything from massive delivery trucks down to maybe small, nimble courier vans.
That's a great way to think about it. Different vehicles for different cargo and different destinations. Each class has its own typical composition, different percentages of tags, cholesterol, protein, which dictates its function.
All right, let's start the tour. Where do we begin? Maybe with the biggest. Chylomicrons.
Perfect. Chylomicrons. Think of these as the dietary delivery trucks.
Dietary. So they handle the fats we eat.
Precisely. They are formed only in the small intestine, in those absorptive cells called enterocytes, right after a fatty meal. Their whole mission is to transport the dietary lipids, the tags, cholesterol, fat-soluble vitamins you just ate from your gut into your system.
Okay, so I eat some fatty food. My enterocytes package it up into chylomicrons. What happens then? How do they get into the blood?
Ah, interesting point. They don't go directly into the blood capillaries in the gut. They start as nascent chylomicrons, carrying a specific apoprotein ID badge called ApoB48.
ApoB48. Okay.
Then they're actually exocytosed, released into the lymphatic system, the lacteals and the intestinal villi.
The lymph, not the blood.
Not initially. They travel through the lymphatics and eventually enter the bloodstream via the thoracic duct, which empties into the subclavian vein. It's a slightly roundabout route.
Okay, so eventually they hit the main circulation. What happens in the blood?
Once in the blood, they need to mature. They acquire more apoproteins, specifically ApoC and ApoE, by transfer from HDL particles already circulating.
HDL gives them ApoC and ApoE. Why do they need those?
ApoC is absolutely critical. It acts as an activator for an enzyme called lipoprotein lipase, or LPL.
LPL, lipoprotein lipase. What does that do?
Think of LPL as being like a toll booth operator, or maybe tiny scissors anchored to the walls of capillaries, especially in adipose tissue, fat storage, and muscle tissue, energy use.
Okay, scissors in the capillaries.
Activated by ApoC on the chylomicron, LPL gets to work hydrolyzing, breaking down the triacylglycerols inside the chylomicron core.
Ah, so it chops up the tags.
Exactly. It releases free fatty acids and glycerol. These fatty acids can then be taken up by the adjacent fat cells for storage or by muscle cells for energy.
So the chylomicron is delivering its main cargo, the tags. What happens as it gets emptier?
As the tags are depleted, maybe down to about 20% of the original amount, the job of ApoC is done, and it actually gets transferred back to HDL.
Gives it back. Okay.
What's left of the chylomicron is now smaller, denser, and relatively enriched in cholesterol and cholesterol esters. We call this a chylomicron remnant.
The remnant. What happens to it?
It needs to be cleared from the blood. The ApoE you picked up earlier now acts as the signal. It binds to specific receptors on liver cells, hepatocytes. The liver takes up these remnants and breaks them down completely.
So the liver cleans up the leftovers from the dietary fat delivery.
Precisely. And here's a really important clinical point for you listening. Normally, chylomicrons are only present in your blood for maybe 4 to 6 hours after a meal.
Okay.
If you take a blood sample from someone who has fasted for, say, 6 to 8 hours or longer, and their plasma looks milky or turbid, that's a big red flag.
Milky plasma after fasting. Why?
It means chylomicrons are still hanging around. They haven't been cleared properly. It points towards a problem, maybe with LPL activity or the remnant uptake process. Definitely something you'd need to investigate further.
Got it. Milky plasma post-fasting equals chylomicron problem. Okay, so that's dietary fat. What about the fats our own liver makes, the endogenous stuff?
Ah, good question. The liver doesn't just clean up remnants. It's also a major site of lipid synthesis, and it needs to ship out the tags it produces. For that, it uses its own fleet, starting with VLDL.
VLDL, very low-density lipoproteins. These are the liver's endogenous TG shuttles.
Exactly. Synthesized in the liver, their primary job is to transport endogenously synthesized triacylglycerols tags made by the liver itself out to peripheral tissues, again, mainly adipose and muscle.
How do they start their journey?
They are released from the liver directly into the bloodstream as nascent VLDL particles. Their main structural apoprotein, their permanent ID badge, is ApoB100.
ApoB100 for VLDL, whereas chylomicrons had ApoB48. Interesting difference.
A very important difference, yes, related to how ApoB protein is processed in the gut versus the liver. But like chylomicrons, nascent VLDL needs to mature in the blood.
Let me guess it picks up apoC and ApoE from HDL,
You got it, same mechanism.
Yeah.
And that apoC activates LPL on capillary walls.
which then hydrolyzes the VLDL's tags, releasing fatty acids for tissues. It sounds very similar to the chylomicron pathway.
It is very similar in that initial stage. LPL works on both. There's also a bit of exchange happening during this process. VLDL can give some tags to HDL, and HDL gives some cholesterol esters back to the VLDL particle, the dynamic process.
Okay, so as VLDL unloads its tags thanks to LPL, what does it become?
As it loses tags and becomes relatively richer in cholesterol esters, it transitions into an IDL particle, intermediate density lipoprotein.
IDL. The transition vehicle, are these around for long?
No, they're pretty short-lived. IDL still has a fair amount of tags, maybe around 30%. It's kind of in between VLDL and the next stage.
And what's its fate?
It'd have two main possibilities. About half of the IDL particles are taken up directly by the liver, again using that ApoE signal binding to liver receptors. There's also another enzyme in the liver called hepatic triglyceride lipase, HTGL, that helps process them.
Okay, taken up by the liver, what's the other possibility?
The other half of the IDL particles remain in circulation and undergo further processing. They lose more tags, primarily through the action of that hepatic lipase. As the tag content drops significantly, down to maybe 10% or so,
Yeah.
the IDL particle sheds its ApoE and apoCAI. They mostly return to HDL. And what remains, now very rich in cholesterol esters and still carrying that structural ApoB100, is LDL.
LDL. Low-density lipoprotein, the famous one, the cholesterol courier.
That's the one, derived directly from IDL in the circulation. LDL's main job is no longer primarily tag transport. Its mission is to deliver cholesterol, mostly synthesized by the liver, to peripheral tissues throughout the body.
Which tissues need this cholesterol?
Lots of them. Any cell that needs cholesterol for building or repairing its membrane, or cells in endocrine glands that use cholesterol to synthesize steroid hormones like cortisol or sex hormones.
How does LDL deliver the cholesterol?
Through a very specific mechanism. Cells that need cholesterol express LDL receptors on their surface. LDL particles bind to these receptors via their ApoB100 ID badge.
The ApoB100 is the key again.
It's the key. Once bound, the entire LDL particle, receptor and all, is taken into the cell by endocytosis. The cell literally engulfs it.
Swallows it whole. Then what?
Inside the cell, the LDL particle is broken down in lysosomes, and the cholesterol is released for the cell to use.
Is this delivery process regulated? Can cells get too much cholesterol?
Oh, absolutely. It's tightly regulated. If a cell has enough cholesterol, it does a few things. High intracellular cholesterol levels actually inhibit the cell's own cholesterol synthesis pathway.
Stops making its own.
Right. And it also downregulates the expression of LDL receptors on its surface. Fewer receptors mean the cell takes up less LDL from the blood.
A negative feedback loop. Clever. Prevents the cell from getting overloaded.
Exactly. It's a really elegant control system to maintain cholesterol homeostasis within the cell.
Okay, so we've traced the path. VLDL from the liver delivers tags, becomes IDL, then IDL becomes LDL, which delivers cholesterol to cells via the LDL receptor. LDL seems pretty essential.
It is essential. Cells need that cholesterol.
Which brings us back to that thought-provoking question I raised earlier. If LDL's job is so vital, delivering necessary cholesterol, why on earth does it have such a bad reputation? Why is it always called bad cholesterol? And, what happens when this whole delivery system gets unbalanced?
Right. That's the million-dollar question, isn't it? And it leads us straight into the clinical side, the good, the bad, and the unbalanced.
So why is LDL bad?
Well, the issue isn't LDL performing its normal function. The problem arises when there's too much LDL circulating in the blood, or when it sticks around for too long.
How long does it normally stick around?
LDL has a significantly longer half-life in the blood compared to VLDL or IDL. We're talking days, not hours.
Okay, so it hangs around longer. Why is that bad?
That longer residence time makes it much more susceptible to chemical modifications, specifically oxidation. Free radicals in the blood can damage the LDL particle.
Oxidized LDL. The damaged goods, as you called it.
Exactly. And this oxidized LDL is where the trouble really starts. It's no longer recognized properly by the normal LDL receptor. Instead, it triggers an inflammatory response.
Oh, so?
Immune cells called macrophages, which are like the cleanup crew of the immune system, have special scavenger receptors that recognize and gobble up oxidized LDL.
They eat the damaged LDL.
They do.
Yeah.
but they don't have that nice feedback regulation that the normal LDL receptor pathway has. So they just keep eating and eating the oxidized LDL until they become engorged with lipid droplets.
Engorged macrophages. What happens then?
They transform into what we call foam cells because of their bubbly, foamy appearance under a microscope.
Foam cells.
The
Okay.
foam cells then start to accumulate within the wall of arteries, specifically in the intima, that layer just beneath the endothelial cells lining the vessel.
They build up inside the artery wall?
Yes.
Yeah.
This initial accumulation of foam cells forms what's known as a fatty streak. You can sometimes see these even in young people.
Fatty streaks. Are they dangerous?
In themselves, maybe not immediately, but they are the precursor lesion. Over time, these fatty streaks can progress. More lipids accumulate, smooth muscle cells migrate into the area, fibrous connective tissue forms, and you get a complex atherosclerotic plaque.
The plaque. That sounds bad.
It is bad. This plaque thickens the artery wall and narrows the lumen, the channel where blood flows. This reduces blood supply downstream.
Less blood flow that causes problems.
Definitely. And worse, these plaques can become unstable. If the fibrous cap covering the plaque ruptures, the highly thrombogenic material inside gets exposed to the blood.
Thrombogenic, meaning it causes clots.
Exactly. It triggers rapid blood clot formation, thrombosis, right on top of the ruptured plaque. This clot can suddenly block the artery completely.
And if that artery supplies the heart.
That's a myocardial infarction, a heart attack.
Or the brain.
That's an ischemic stroke. If the blockage is partial or temporary, it might cause angina, that chest pain from lack of oxygen to the heart muscle.
So oxidized LDL foam cells, fatty streaks, plaques, rupture, clot, heart attack, or stroke. That's the bad part.
That's the cascade, yes. And another important point, research suggests that having a higher number of small, dense LDL particles might be even more atherogenic, more likely to cause plaques, than just having a high total LDL level. They seem to penetrate the artery wall more easily and get oxidized faster.
Wow. So it's not just the amount, but the type of LDL too. Okay. If LDL is potentially bad, surely there must be a counterbalance, a good guy in this story.
There is. Meet HDL, high-density lipoprotein, our dedicated reverse cholesterol cleanup crew.
HDL, the good cholesterol. Where does it come from?
It's mainly synthesized and secreted by the liver and the intestine. It starts out as a rather empty disc-shaped particle called nascent HDL, primarily containing the apoprotein ApoAI.
Nascent HDL, like a little empty disc.
Yeah, almost like a flattened sphere initially. It can also acquire components like phospholipids and ApoA that are shed from chylomicrons and VLDL as they get broken down by LPL, so it kind of recycles parts.
And what's its big mission? Why is it good?
Its main role is incredibly important. Reverse cholesterol transport, or RCT.
Reverse transport, taking cholesterol back.
Exactly. HDL's job is to scavenge excess cholesterol from peripheral cells, including those foam cells in the artery wall, and transport it back to the liver.
Takes it away from where it can cause damage.
Precisely. The liver can then excrete this excess cholesterol from the body, usually after converting it to bile salts, which are released into the intestine.
So HDL cleans up the mess. That's why it protects against atherosclerosis.
That's the key mechanism. By removing excess cholesterol from cells, especially macrophages in the artery wall, HDL helps prevent or even shrink atherosclerotic plaques. It minimizes foam cell formation.
Okay, how does it actually do that? How does it pick up the cholesterol?
It's a multi-step process. First, that nascent disc-shaped HDL interacts with peripheral cells. There's a special protein on the cell surface called ABCA1, ATP binding cassette transporter 1.
ABCA1.
ABCA1 actively pumps excess free cholesterol out of the cell and onto the nascent HDL particle.
So the cell basically hands over its extra cholesterol.
Yes. Now, once this free cholesterol is on the HDL particle, it needs to be trapped there. This is where another key player comes in, an enzyme called LCAT, lecithin cholesterol acyltransferase.
LCAT. What does it do?
LCAT circulates in the blood, associated with HDL. It's activated by ApoAI on the HDL surface. LCAT takes the free cholesterol and attaches a fatty acid to it, converting it into a cholesterol ester.
Why esterify it?
Cholesterol esters are much more hydrophobic than free cholesterol. So as soon as they're formed, they move from the surface into the hydrophobic core of the HDL particle.
Ah, tucking it away inside.
Exactly. And as more and more cholesterol esters accumulate in the core, the HDL particle swells up and becomes spherical. It goes from that flat disk to a mature, round HDL particle. It's literally filling the cleanup truck.
That's brilliant. So it collects cholesterol via ABCA1, traps it inside using LCAT. What happens next? Does it just go straight back to the liver?
It mostly heads back to liver, but there's another interesting interaction first. There's a protein called CETP, cholesterol ester transfer protein.
CETP, what does it do?
CETK facilitates an exchange. It can transfer cholesterol esters from HDL to VLDL particles, or IDL-LDL.
HDL gives its cholesterol esters to VLDL. Why? That sounds counterintuitive.
In return, CETP transfers triacylglycerols from VLDL to HDL, so it's a swap. Cholesterol esters for tags.
A lipid exchange program, what's the point of that?
It's complex, but one effect is it allows some cholesterol collected by HDL to eventually end up in LDL particles, which are then cleared by the liver via the LDL receptor. There's another route back to the liver. However, high CETP activity can sometimes be detrimental, leading to lower HDL and smaller LDL.
Okay, so some complex trading happens, but ultimately, how does the main load of cholesterol get back to the liver via HDL?
The mature cholesterol ester-rich HDL particle primarily interacts with the liver via another receptor called SRB1. Scavenger receptor class B type 1.
SRB1 on the liver cells.
Right. SRB1 allows the liver to selectively take up the cholesterol esters from the HDL core without taking up the entire particle. The HDL particle can then go back out and collect more cholesterol.
Efficient recycling. And the liver then gets rid of that cholesterol.
Yes, typically by converting it to bile acids or excreting it directly into bile. Also, steroidogenic tissues, like the adrenals and gonads, can use SRB1 to grab cholesterol from HDL to make their hormones.
Okay, so HDL really is the good guy running around cleaning up excess cholesterol.
Fundamentally, yes. Higher levels of functional HDL are generally associated with lower cardiovascular risk.
Which brings us to when things go wrong. What do we call it when this whole system LDL delivery HDL cleanup is out of whack?
The general terms are dyslipidemia, meaning abnormal lipid levels, or hyperlipoproteinemia, meaning elevated levels of specific lipoproteins. Basically, the system's off balance.
What causes these imbalances?
It can be a combination of factors: genetics, diet, lifestyle, other diseases like diabetes or kidney disease. Fundamentally, it's often due to either the body overproducing certain lipoproteins or under-removing them from the circulation.
Under removal?
Yeah.
Like problems with receptors or enzymes?
Exactly. Defects in key players like the LDL receptor or the LPL enzyme, or even in apoproteins like ApoE, can lead to specific patterns of dyslipidemia.
Is there a way to classify these?
Historically, the Fredrickson classification, which the WHO adopted, was widely used. It categorizes hyperlipoproteinemias into different types, I through V, sometimes with subtypes like II and II, based on which lipoproteins are elevated.
Does that help clinically?
It helps understand the underlying pattern. For instance, type BIA, also called familial hypercholesterolemia, is characterized by very high LDL levels, often due to defective LDL receptors. It carries a very high risk of premature coronary artery disease.
High LDL, high risk. Makes sense. Any others worth noting?
Type 3, dysbeta-lipoproteinemia, is another important one. Here you see elevated levels of both IDL and chylomicron remnants. It's often due to defects in ApoE, which, remember, is needed for clearing these remnants. This type also significantly increases risk for coronary and peripheral artery disease.
So, problems with ApoE mess up remnant clearance. Got it. Can you actually see signs of high cholesterol on a patient?
Sometimes, yes, especially if the levels are very high or have been high for a long time. You might see xanthelasma.
What are those?
They're yellowish patches, slightly raised, that appear on or around the eyelids. They're cholesterol deposits in the skin macrophages there.
Okay, yellow patches on eyelids. Anything else?
Tendinxantomas. These are harder nodules, actual cholesterol accumulations within tendons. The Achilles tendon behind the ankle is a common site, or tendons in the hands. Feeling those can be a strong clue.
Nodules on tendons. Wow.
And sometimes, corneal arcus. This is a whitish or grayish ring that appears around the edge of the cornea, the clear part of the eye.
A white ring in the eye.
Yes, it's caused by lipid deposition. Now, it's quite common in older adults and might not mean much then, but seeing a significant corneal arcus in someone younger, say under 45 or 50, is much more suggestive of underlying hypercholesterolemia.
Xanthelasma, tendinxantomas, corneal arcus in younger people, visual clues.
Yeah.
Okay, so if we identify dyslipidemia, how do we treat it? How do we restore the balance?
The first step, always, is lifestyle. It's the foundation.
Diet and exercise.
Absolutely. Diet is key. Reducing intake of saturated and trans fats, cutting down on dietary cholesterol, and importantly, increasing dietary fiber, especially soluble fiber.
Why fiber?
Soluble fiber can help lower LDL cholesterol, partly by binding bile acids in the gut. Then lifestyle changes. Regular physical activity is crucial, losing excess weight if needed, and definitely stopping smoking. Smoking damages blood vessels and worsens lipid profiles.
So diet, exercise, weight management, no smoking. What if that's not enough?
If lifestyle modifications alone don't bring the lipid levels, particularly LDL cholesterol, down to target goals, then we move to pharmacological intervention medications.
And the big players here are the statins, right?
Statins are the cornerstone, yes. Drugs like atorvastatin, simvastatin, rosuvastatin, they are incredibly effective at lowering LDL cholesterol.
How do they actually work? What's the mechanism?
They are cholesterol synthesis inhibitors. They work primarily in the liver by blocking a key enzyme called HMG-CoA reductase.
HMG-CoA reductase. That's early in the cholesterol-making pathway.
It's the rate-limiting step, yes. By inhibiting this enzyme, statins reduce the liver's own production of cholesterol.
Less cholesterol made by the liver. How does that lower blood LDL?
When intracellular cholesterol levels drop in the liver cells, the cells respond by upregulating the number of LDL receptors on their surface. More LDL receptors mean the liver pulls more LDL cholesterol out of the bloodstream for processing.
Ah, so they lower production A and D, increase clearance. Double effect.
Exactly. That's why they're so effective at lowering LDL.
Are there other types of drugs used?
Yes. Several others can be used, sometimes in combination with statins or statins aren't tolerated. One older class is the bile acid sequestrants or bile salt binders, like cholestyramine or cholestyramine.
Bile acid binders. How do they work?
They're resins that you take orally, and they stay in the gut. They physically bind onto bile acids in the intestine, preventing them from being reabsorbed back into the liver, a process called enterohepatic circulation.
So the bile acids get excreted instead.
Right. And since bile acids are made from cholesterol in the liver, losing more bile acids forces the liver to use up more of its cholesterol pool to synthesize new ones. This, again, leads to upregulation of LDL receptors to pull more cholesterol from the blood.
Clever way to force the liver to use up cholesterol.
It is. There are other drug classes, too, like ezetimibe, which blocks cholesterol absorption in the gut, and newer injectable drugs like PCSK9 inhibitors, which dramatically increase LDL receptor availability. But statins and sometimes sequestrants are often the first lines after lifestyle.
Okay, so wow, we've covered a lot of ground.
We really have. It's been quite the journey.
Yeah, from understanding, just how diverse lipids are and that basic problem of them being hydrophobic.
To the solution.
No.
These incredibly sophisticated lipoprotein taxis.
Right. The different classes, chylomicrons, VLDL, IDL, LDL, HDL, each with its specific job, its specific apoprotein ID card.
Navigating those complex routes, interacting with enzymes like LPL, receptors like the LDL receptor, and SRB1.
And then connecting all that amazing biochemistry and physiology to the really critical clinical stuff like atherosclerosis, the whole good versus bad cholesterol idea.
And how dysregulation leads to disease, but also how we can intervene with lifestyle and medications like statins.
For everyone listening, especially if you're heading into clinical years, really try to lock this down. Understanding these pathways, it's not just academic hoop jumping.
Not at all. It is fundamental. It underpins how you'll diagnose, manage, and even help prevent some of the most common, most impactful diseases you'll ever encounter: heart disease, stroke.
It's that direct link between the biochemistry of lipid transport and the actual health, the lives of your patients.
Couldn't agree more. It's foundational knowledge.
Okay, so to wrap up, as always, we want to leave you with a final thought, something to chew on.
Go for it.
All right, consider this. You have a patient. Their total cholesterol level comes back reported as normal, okay? But when you look closer at the breakdown, their HDL is very low and their triglycerides are quite high.
Okay, normal total, but low HDL, high tags.
Yeah. What does that specific pattern, that ratio of lipids, tell you about their actual cardiovascular risk, even with a normal total cholesterol? And maybe more importantly, why is that pattern, that balance between the different lipid fractions, often so much more revealing than just looking at a single total number?
Ooh, that's a good one. Thinking beyond just the total cholesterol. Looking at the whole picture. Excellent food for thought.